we want to find the local stiffness matrix in the global coordinate system. In this video, I'm going to find the local stiffness matrix in the local coordinate system, and we'll also define the transformation matrices that allow us to go back and forth between the local coordinate system and the global coordinate system. In the next video, we'll use this and some linear algebra to derive the local stiffness matrix in the global coordinate system. Let's refresh our memory about this diagram that I drew before. I'm visualizing some large three-dimensional truss, and this blue bar is some bar that exists inside this larger three-dimensional truss. It's a single bar element. When I defined my larger truss, for the convenience of solving that particular problem, I chose a global coordinate system x, y, and z. This particular bar has some generic orientation that's not along the x, y, or the global z-axis. It's got its own orientation. I'm defining the length along that bar x hat as the local coordinate system. There's also a y hat and a z hat, but in a bar element, all the forces applied to it and all of its displacements will be along the x hat direction. So in the local coordinate system, the x hat direction is the only direction I care about. I've got forces applied to it at each end. I've also, these forces are causing displacements u1 hat and u2 hat. Now I've defined three angles. These angles extend from the x hat vector to a corresponding global coordinate axis. So theta x goes from the x hat vector to the global x axis. Theta y goes from the x hat direction to the global y axis, and theta z goes from the local x hat direction to the global z axis. All right. Now I said in the last video, our first step is to define the local stiffness matrix in the local coordinate system. We've already done that in 1 dimension. Remember, in 1 dimension, and I'm just going to kind of use 1 dimension in the local coordinate system is just our x hat direction. So what I'm saying is if I have u hat 1 and I know the displacement u hat 2, and I want to know what forces apply to cause these displacements, that's f1 hat and f2 hat, then I'll multiply this by a matrix, and that's our local stiffness matrix in the local coordinate system. We already derived it. It's the scalar constant EA over L times a vector 1, 1, negative 1, negative 1. And of course, it's 1-dimensional. There's no angles, and this is always what the 1-dimensional stiffness matrix looks like. Since we're dealing with just the x hat axis, I'm going to leave this as a 2 by 2. So you'll remember last week when we looked at the 2-dimensional case, I kind of blew this up and turned it into a 4 by 4 by adding in a bunch of zeros. In the next video, when I do the linear algebra, it'll be easier if I leave this as a 2 by 2 matrix. So done. Job done. This is our local stiffness matrix and the local coordinate system. All right, now let's take a look at what I have going on here. What I have going on here is I'm saying that there is some generic vector u hat, which has a length u hat, has a length extending from here to here. So its length is u hat. And it's some vector that's in the direction of x hat. Okay? It could be a displacement. It could be u1 or u2. It could equally be u1 hat or f2 hat. I'm sorry, f1 hat or f2 hat. Okay? But it's along the x hat axis. If I wanted to describe it in the global coordinate system, I would need to decompose its length in the x direction, its length in the y direction, and its length in the z direction along the decomposed length of the global coordinate system. I'm going to call this length along the x axis u. I'm going to call this length parallel to the z axis W, and this length parallel to the y-axis I will call V. Now, from the way I defined theta x, theta y, and theta z, I hope you can see that my length, u, is simply equal to the length of u hat times cosine of theta x. And likewise, v equals the length of u hat times cosine theta y, and w equals the length of u hat cosine theta z. Okay? Now, in what follows, I'm going to have to write cosine theta x, cosine theta y, and cosine theta z quite a few times. So I'm going to be lazy and do what the book does, and I'm going to shorthand that to cosine theta x is simply cx, cosine theta y is simply cy, and cosine theta z is simply cz. Okay? Now that I understand that, suppose I had this, my local displacement vector in the local coordinate system. u1 hat and u2 hat. And I want the local displacement vector in the global coordinate system. But what I'm saying is what I want is this vector, u1, v1, w1, the displacements of node 1 defined in the global coordinates, over u2, v2, w2, the displacements of the node 2 defined in the global coordinate system. I can get this vector from this vector simply by defining this 6 by 2 matrix, where the elements along here, which will get multiplied by u1, are cx, cy, cz. I don't want anything multiplied by u2, so I'll put zeros here. Likewise, to get these values, I don't want anything multiplied by u1 hat. I just want this relationship by u2 hat, so this will be cx, cy, cz, 0, 0, 0. All right? Now let's look at this the opposite way. Suppose I want this, and I have this. I can do the transformation from here to here by multiplying by this 2 by 6 matrix, cx, cy, cz, 0, 0, 0, 0, 0, 0, cx, cy, cz. The derivation of this matrix to go from the global coordinate system to the local coordinate system was done in the book. All right? But as you can see, this matrix and this matrix are the transforms of each other. So to use the same notation as the book, I'm going to call this matrix T star. And I'm going to call this matrix the transform of T star. All right? And we will use these two transformation matrices in the next video to find the local stiffness matrix in the global coordinate system.